Hello, everybody. My name is Boris Botvinnik, and would like to continue with the second part of my talk, Topology of Spaces and Moduli Spaces of Metrics with Positive Scalar Curvature. Part 2. Okay. In the first part, we defined the index difference map, which goes from if we fix a base point in the space of metrics of positive scalar curvature, then there is a map going from the space of metrics to the space loop space of space of Fredholm operators, Clifford linear, which classifies K-theory. And the theorem, which are main theorem I would like to explain, at least the ideas and technique behind this, which is by myself, Johannes Ebert and Oscar Randall Williams, is the following. If W is a spin manifold, let W be a spin manifold with dimension at least 6. Actually, it's true if dimension at least 5 as well. And G0 is a base point, then the homomorphism, the index difference map, induces homomorphism in homotopy groups, which is non-trivial, non-zero whenever the target group is non-zero. And then here again, I would like to mention that if target is Z mod 2, it means that it's onto. If target is Z, in general, it may be not onto, but we show that it's onto up to some degrees, and otherwise it's reduced. It is reduced to some problem in number theory. Also, I would like to emphasize again that there are much stronger results on the space of space of positive scalar curvature metrics. If manifold has non-trivial fundamental group, then the target will be in K-theory of corresponding C-star algebra, reduced C-star algebra on this fundamental group. Okay, now in order to show some ideas, relevant ideas, I have to introduce new characters, namely moduli space of metrics. Moduli space of metrics. If we start with connected spin manifold, spin is actually not quite important here. It is in a sense for these particular definitions, but connected is important. Then we take our space of metrics, all space of metrics with which is product near the boundary and which restricts to given metric on the boundary. For convenience, we assume that this metric has positive scalar curvature on the boundary. Then there is a group of diffeomorphisms which act on space of metrics by pulling back, and then we look at the all diffeomorphisms which are identity near the boundary. And there is observation here, important observation, that this group acts freely on the space of all metrics and also on the space of metrics of positive scalar curvature. This is not very sophisticated fact. However, I would like to show why this is actually true. So if we assume that phi star of G is G, the same metric, then what we can do, we can look at any point X, choose a point X0 on the boundary, and find a geodesic which joins these 2 points. And then we notice that near the boundary, this geodesic will be preserved because our diffeomorphism group is identity. And then we can actually go along this geodesic carefully and then see that G will preserve the whole geodesic excuse me, diffeomorphism will preserve the whole geodesic, and in particular, G of X, phi of X will be equal to X. So this is actually identity. Similarly, there is a relevant construction for manifold without boundary, but then we have to think in terms of a little bit different group when we have to fix some point on the bound on the manifold, and then think about all diffeomorphism which are identity near this point. Then the similar result holds as well. Okay, now I would like to emphasize one particular property here, that there is a fiber bundle. So what we have here, we have that we have all metrics on W. Then we have space of modular space of all Riemannian metrics, which is the same as classified space of our group, and up to homotopy because our space is of all metrics is convex, and then we have also a space of modular space of all positive scalar curvature metrics, and here we have space of the space of positive scalar curvature metrics. We have a diagram like this, which is commutative, and this both vertical maps are fibers, principal fibers with the fiber group. And if you look carefully, we use the fact that this is a contractible convex space. Then we can identify the space of all metrics of positive scalar curvature with the fiber of this particular map. This is a good exercise in kind of basic algebraic topology. Now, so this is what I defined then before, that this is the space of all modular space is the same as the space of classified space for the diffeomorphism group diff del of W, and we define this one. Now, then what we see that there is a fiber bundle in particular with a base. This is the same again. There's a modular space of all Riemannian metrics with the given boundary metric on H0 on metric H0, and this is a fiber bundle. I would like to say a couple of make few remarks about modular spaces. As we have seen, the spaces of positive scalar curvature metrics are homotopy equivalent for all spin simply connected manifolds of given dimension, and of course we mean that they're spin, and then but the spaces of modular spaces of PSC metrics actually could be very different, and we know not much about these spaces, by the way. This is a widely open question, and in particular we know not much about the classified space of diffeomorphism group for arbitrary manifold W. Again, for some special manifold, special cases we know, but we do not know what would be which topological properties could be preserved if we look at the map from space of modular space of all positive scalar curvature metrics to the classifying space. However, for particular space, particular manifold, W and W is a disk, and H0 is a standard metric on its boundary. We have there is a following result, which is done 10 years ago, that the map, this map we defined before, induces epimorphism or surjection in homotopy groups, rational homotopy groups in some wide range of for a wide range, so-called stable range. Okay, now let's take a look again at our fiber bundle, this fiber bundle. And there is a standard construction from algebraic topology. What we do, we take a loop in the base, then we choose, of course, a point which goes to this base point, which is a metric, our metric, we choose base point in the space of all metrics of positive scalar curvature, and we leave this loop. And then what we see that there is it goes back to this space of metrics of positive scalar curvature. And moreover, this loop can be described as applying some diffeomorphism phi t to tilde to metric G0. And so then in particular, this metric and G0 and this metric are connected by diffeomorphism phi1. Then what we can do, we can look carefully at the, so we look at the cylinder and construct metric, which is phi1 of GT. G0, actually, phi t of G0, and then we have again metric on the cylinder, which is a product metric near the boundary, and we can evaluate index of the corresponding Dirac operator of this metric G bar, and we obtain a map from loops of this classifying space of group of diffeomorphisms to the loops of Fredholm operator. And now we need some examples, particular examples. And we start with, say, manifold, which is very simple. It's a just disk of dimension 2n. And by the way, I will restrict my attention to only even dimensional manifolds, and this for the purposes of this talk. And then what we can do, we can attach a cylinder with Sn cross Sn connected sum. And then in this new manifold, we see that we can go back and forth in terms of metrics of positive scalar curvature. By the way, on the boundary, we have a standard metric, and here again, we have standard metric. So for each metric here, there is a metric which is, we say, choose some standard metric on the cylinder. And then there is a homotopy equivalence between these two spaces, What we can do, we can actually extend this construction and start with our disk, again, dimension n, with the same standard metric on the boundary, then attach this connected sum, the cylinder with Sn cross Sn. And then we choose corresponding metrics of positive scalar curvature on each cylinder. We can maybe the same. And then we have new manifold. So we define manifold WK minus 1. This is we attach all this K minus 1 cylinders with Sn cross Sn attached. And then WK, we have WK is WK minus 1 and one more cylinder VK. VK. And also we have a standard, we can extend metric and we obtain the following interesting composition. So that what we have a, if we choose a metric G here, any metric positive scalar curvature, then and any metric G prime over there, then we can extend it to a metric G and attached to metric G prime. And the reason is because here we have always metric, standard metric on the sphere. And if we fix metric GK over there, then there is a map from the space of metrics on the positive scalar curvature metric on WK minus 1 to the space of metrics of positive scalar curvature on WK. And the because of we know that this type of attachment is equivalent to surgery, it's easy to conclude that this is actually a homotopy equivalence. Okay, so again, let's take a look again at this diagram, and then we have our manifolds. So we have WK minus 1 embeds to WK, embeds to WK plus 1. And so let's think about this as a kind of stabilization process. And notice that corresponding diffeomorphism groups also there is a natural embedding, because if you have a diffeomorphism which is identity near the boundary, we can extend it by identity to the next piece. And so then in particular what we have a corresponding spaces of classifying spaces of diffeomorphism groups. And by the way, these are nothing but spaces of moduli spaces of all metrics, such that which have standard metric on the boundary and product metric near the boundary. Again, so what does it mean is that we have a map not just of a fiber band of fibers of the classified spaces, but we have a map of corresponding fibers, fiber bundles. And what is also very important for us, that fibers are the same up to homotopy equivalence, So what's going on is we can take a limit of this fiber bundles to get new fiber bundle over the limiting space, which we have classifying spaces of this diffeomorphism group. And not much we can say immediately about the total space, but we know for sure that the fiber is just, has the same homotopy type as the space of metrics on the original disk with a standard metric on the sphere. And then what else is important, that we still have this holonomy map. So again, we take a loop on the base which is B infinity, and we lift it, and we get new element in the fiber. And moreover, this evaluation map, so there is also index map. We can think about index map, which you define. You can define using using index maps on the, before the index map on the fiber, as before. Then there is a map. So this is we have pre-limiting space. This is homotopy equivalence, and this is just the same object. And then what is crucial point here now is that the limiting space has been understood in some sense. Namely, in the beginning of 2000, Ibmatson and Mike Weiss introduced new technique, namely so-called parameterized surgery, which allows to describe various moduli spaces of manifolds. And this subject would deserve, a special workshop. But the result we need is the following. This result is due to Soren Galatius and Oscar Renda Williams, that there is a map, this is a natural map, from this limiting space to the space on the right, which is actually, this is a Thom, some kind of Thom spectrum, and this is infinite loop space, and we take only the one path component. But as we'll see, what is important that this space is not, you can identify with the space of all 2n dimensional n-1 connected manifolds. And also a couple of remarks here that this space is has highly non-trivial fundamental group. This space has trivial fundamental group. So, and however, this map induces isomorphism in homology group. Moreover, it's actually acyclic. And it's a real magic here that this is true. This allows us to construct and to push forward this fiber bundle over B infinity to fiber bundle over this space of manifolds, 2n dimensional manifolds and -1 connected manifolds. And also we have again similar holonomy map. And moreover, there is one more magic here, that for each element here, we can consider as 2-dimensional, 2n dimensional manifold, which is n-1 connected. And then what we do, we take this manifold and look at corresponding Dirac operator on this manifold, since it's spin, and we get a map to, again, to space of Dirac operators. And now, next step, index theory, which is we had to analyze several aspects, different aspects of index theory, shows that this diagram is commutative, namely, so this holonomy map composed with holonomy, so this map to space of Fredholm operators. Actually, factors through evaluation map, holonomy map to the space of matrix of positive scalar curvature, we take index. And then the whole point is the following, that this map is you can compute by means of more or less standard algebraic topology. And if we know that it's non-trivial, then we know that it factors through unknown space of matrix of positive scalar curvature. And then if it's, so then the corresponding map here induces also non-trivial map in homotopy group. And I would like to put some references. This is the paper where we prove this result. Then this is the paper where we show that the modular space of matrix of positive scalar curvature could be understood for the disk. And these two papers are quite important here because Johannes put together several different aspects of index theory to so that the magic of index theory would work. And this last paper is where Johannes and Oscar generalized this technology to manifolds with non-trivial fundamental group, and where there are very interesting results. Thank you very much. I appreciate your attention, and I hope to get some questions.